Here for this wonderful introduction to Rohini's achievement. Now let me start by the first talk to discuss more about her scientific work. So I will tell you about topics that were dear to her heart, so supersymmetry, Higgs, and later on dark matter, and it's work that was carried out over 25 years, mostly through exchange visits to France and India, and many of them under the Indo-French projects that we shared for many years. So I will not give you a full introduction to supersymmetry, but remind you that 20 years ago, supersymmetry was the best, most favored extension to the standard model because it showed a way so we could have unification of all interaction and predict the light Higgs and solve the hierarchy problem. And furthermore, it had R parity that protects proton decay, made that the lightest supersymmetric was stable and could be dark matter. So let us go back a few years. The Higgs was not discovered, and the question we asked on our first visit to India, so this was me, my son, and also Fauzi was there. You cannot see Rohini because she's taking the picture. And what we were worried about is, will the LHC discover the Higgs in all possible supersymmetric scenarios? And why we were worried about that, because we realized if supersymmetry was lightish, 100 GeVs or so, it could affect the Higgs signal. Because we already knew that we had limits on supersymmetric particles around 100 GeV from LAPTh. But if you add some light supersymmetric colored particle, it could change the Higgs production through gluon. And if you had some light charged particle, it could change the Higgs decay into 2 photons. Or even if the neutral particles were light enough, the Higgs could decay into neutral particles, the neutralinos, and becomes invisible. And what we showed in this paper is that even if this happened, then you could necessarily would see some signal of new physics through the production of supersymmetric particles. So we had no reason to worry about that because the Higgs was found, but still this paper with Rohini was very important for many reasons, because this was one of the few phenomenological papers that started looking at non-unification of gauge genome mass. I mean, before everybody was assuming that the gauge genome mass were unified at the high scale, which meant that basically the lightness neutralino was half the mass of the charged genome. So since the charged genome was heavier than 100 GeV, neutralino had to be heavier than 50 GeV. Once you relax this assumption, we realized that it had strong impact on SUSY phenomenology, and there was a possibility of a Higgs decaying invisibly. I'll come back to that later. Another important thing about this paper, at least for us, is that we realized the importance of dark matter, because if neutralino were light, they could overclose the universe unless there were some light fermion, or they could annihilate through a resonance. I'll come back to that later. So because of the importance of that, after writing this paper, we decided that it was very timely to write actually a code which later became micromega to compute the dark matter property in extension of the standard model. So we start with supersymmetry and then extend it to any possible extension of the standard model. So that was a direct follow-up of this first work. Okay, so our worry was still how much invisible decay of the Higgs could be possible, and Rohini even wrote a paper with Manoranjan and company to suggest a new way to search for invisible Higgs LHC via the associated production. At the time, in 2000, we could still have a large invisible width of the Higgs. So here is a plot in the mu-m2 plane of the constant curve showing how large invisible Higgs could be, and could be up to even 60%. After the Higgs was found, of course, the possibility of decaying invisibly was strongly constrained, but still it is possible to have the Higgs invisible. And over the years, we just studied how much the progress in experiments, basically measurement property of the Higgs at the LHC, as well as direct detection of dark matter, affected the the possibility of the Higgs decaying invisibly, or the possibility of having a light neutralinos. So this is a story that ends this year. So let me go through it quickly. So when I talk about a light neutralino in the next few slides, I mean neutralino below 60 GeV, so the Higgs could possibly decay into it. So we know it has to be dominantly below the partner of the U1 gauge boson, because otherwise there would be a charge partner that would have been visible at LAPTh. For it to annihilate, it needs to couple to the Z or the Higgs, and this requires some Higgsino component, either for coupling to the Z or the Higgs. So after the first constraints from the LHC on supersymmetry, looking for the Higgs property, measuring the Higgs decay into various channels. So in 2013, we concluded that the invisible Higgs could be at most of the order of 25%, and that meant that the neutralino would have to be at least about 20 GeV. So what you have to look at here is the orange region, which show the allowed space for the neutralino mass, and the prediction for the spin-independent detection relevant for dark matter search. Over the year, the measurements for especially direct detection and Higgs property improve. And in 2017, we were left with the possibility of having a neutralino around 45 GeV or 60 GeV, so that it would annihilate through either a Z boson exchange or a Higgs exchange. And in 2000, the invisible decay of the Higgs could be at the level of about 10 to minus 2 or 3 around the Z pole, and much lower when you get close to the Higgs because of kinematic suppression. In 2024, at least assuming mu positive, the Z pole disappeared, and basically we were left with the possibility of having a Higgs around, a neutralino around 60 GeV, and the prediction for the spin-independent cross-section, which is plotted here, was just below the latest limits from LZ. This could be expanded a little bit if you allowed some uncertainty in the calculation on the relic density, and there were a few points where you would have a neutralino around 45 GeV. But at the end of 2024, came a new measurement by LZ that told us that everything above this line here is now excluded. So no more possibility of the light neutralino, at least in the MSSM with mu positive. There was still a few possibilities in the case where mu is negative, because when mu is negative, you have different relation of the couplings of the Z or the Higgs to neutralino. And in that case, there was a possibility still of having 45 GeV or even 60 GeV. So this is plotted again in the prediction for the spin-independent cross-section. And on the right is the same plot for the spin-dependent cross-section. So the Z mediates the spin-dependent interaction. So the prediction here are much higher. And again, newer measurements from LZ that basically ruled out the green region here, which is the one which is left after including the latest result from the search for neutralino and chargino at LHE. So everything is ruled out. And there was also a new result from Panda X that basically ruled out also the possibility of having 45 GeV. So after including everything, I can say that no more possibility of light neutralino in the MSSM in 2024. So the question is this a general conclusion? Is this related to the MSSM, or is this happen in any model which has a light sort of singlet, doublet mixing between a singlet, doublet new particle? So this is work that was planned to be done with Rohini. The other way to get around this conclusion is to look at the possibility of having additional states. So that several years ago also we looked at the light neutralino in an MSSM, which is an extension of the MSSM with having a new singlet particle, a new singlet superfield, which implies a new scalar, a new pseudoscalar, and a new part of the neutralino, which is called the synglino. So now there's, again, the same idea. There's possibility of efficient annihilation near a resonance. The synglino annihilates near the resonance of a new singlet state, which is actually not much constrained. So you can get to neutralino mass down at the GeV scale without any problem. And you see the correlation between the mass of the new pseudoscalar here and the mass of the neutralino. So it's basically just half of that mass, except when you get near 45 GeV because you have the Z, near 60 GeV because you have the Higgs. And there are a few points here which actually correspond to the mass of the new scalar to be twice the mass of the neutralino. Okay, so this is a plot of the possible values for the mass of the neutralino that cover a wide range, and most of them are associated with in blue and green with a largely synglino dominated dark matter. So in addition of having a new channel for dark matter annihilation, there's new channel for Higgs invisible, because now the normal Higgs can decay into two Higgses or two light scalar or two pseudoscalar. I should also make a remark is that dark matter below 10 GeV face severe constraints from measurement of the CMB, because dark matter annihilation causes ionization of the plasma, release electron which scatter on CMB photons and cause anisotropy in the CMB. So usually there's a strong bound which says that anything below 10, any particle that annihilates through S wave and is below 10 GeV is ruled out by CMB. In our case, we can avoid these constraints because neutralino annihilates through P-wave annihilation, which is suppressed at very small velocity. So, but still, there's possibility of this resonance annihilation, which is velocity dependence. So, but for very narrow resonance, it was pointed out quite a while ago that it's possible to have a strong enhancement of dark matter annihilating in the galaxy if you tune the parameters such that you have the maximum enhancement at small velocity, while when you calculate the relic, there's a lot less enhancement. So actually, in our study, we found such points, but they require very fine tuning, so they're very, very tiny. So there are a few points which are actually ruled out by indirect detection, but in most cases, it's totally hopeless. So this is a summary of what can be found in the NMSSM. So all the points in different colors are allowed, and you see that. So the current limit is close to this one here, that there's lots of possibility of light neutralinos even below 10 GeV in this model. And this could lead to very small Higgs invisible that could be even below what would be reachable in, for example, the CPC or the FCC edge, especially if dark matter is light. Spin dependent can help a little bit, but not much. In orange are the points which do not satisfy the constraints for spin independence. So basically, the case M that the mass neutralino is less than 10 GeV is hard to cover by direct detection because they lose sensitivity in this region. Even though future projects will help cover this region here above the neutrino floor, but below for the very light neutralino, there's not much hope. So what would be the hope? Well, we turn to the expert on SUSY at Collider, Rohini. And what we found is actually by Higgs and SUSY search in the next version of LHE, we could actually cover almost every possibility. So we just have to wait a few tens of years before we know the final answer for the neutralino. So basically, this implies search for light scalar in Higgs decays, which have some sensitivity, and direct search for neutralino and chargino, and in particular to the three lepton channel. Chargino decays into neutralino and lepton, and heavier neutralino decays to lighter one plus Z or plus H. And this is basically the area that can be covered. So the plots show only the result for the WH mediated case, but basically all this can be covered at HL LHE and HE LHE all can be covered, and this little area not covered, which is not in green, is covered by WZ. And this is an example of a case where a neutrino is only 3 GeV. So one of these hard-to-get neutrino can be probed here. Okay, so that's summary. There's no more room for like neutrino in MSSM. Still possible in an NMSSM. And this is in the standard cosmological scenario. Of course, if you go to non-standard cosmological scenario, relax, Rayleigh density constraints, a lot of possibility are left. And I leave you with this slide to thank Rohini for her magical contribution to particle physics and her commitment to support women in science.
Thanks for doing it.